Hello and welcome to 9.10, Taylor series and Maclaurin series. Okay, Taylor series. Theorem 9.22 says the form of a convergent power series if f is represented by the power series f of x equals the sum of a sub n x minus c to the n for all x in an open interval I containing c, then a sub n would be the nth derivative of f at c over n factorial, and f of x would be represented by this expression f of c plus f prime of c x minus c plus f double prime of c over 2 factorial x minus c squared all the way to the nth term and then beyond. Now the definition of the Taylor series: if a function f has derivatives of all orders at x equals c, then the series n goes from 0 to infinity if the nth derivative of f of c over n factorial times x minus c the n power is, it's like we saw, f of c times f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus dot 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 plus the nth derivative of f at c over n factorial times x minus c to the n power plus dot 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 goes on. It's called the Taylor series for f of x at c. Should look familiar to you. Moreover, if c equals 0, then the series represents the Maclaurin series. So remember, if c is 0, you get the Maclaurin series. We talked about this, I believe it was 9.7. Okay, example 1, use the definition to find the Taylor series centered at c for the function f of x equals cosine x. So, first of all, f of x equals cosine of x. F of pi over 4 equals square root of 2 over 2. F prime of x equals negative sine x. F prime of pi over 4 is negative square root of 2 over 2. F double prime of x equals negative cosine of x. F double prime of pi over 4 is going to be negative square root of 2 over 2. F triple prime of x equals sine of x. F triple prime, it's 3 primes, of pi over 4 equals square root of 2 over 2. I hope we see a pattern here. And that's what we're after here. So look, how far do we have to actually go? Look for a pattern. Fourth derivative of f of x is cosine of x. The fourth derivative at pi over 4 is square root of 2 over 2. Excuse me. So our cosine of x could be written as the sum, as n goes from 0 to infinity, of the nth derivative of f at pi over 4 over n factorial times x minus pi over 4 to the n power. And we see square root of 2 over 2 in all these. So if I just factor it out in the beginning, what we're really going to have to deal with is a 1 and a minus 1, minus 1, 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. So I'll do square root of 2 over 2 out front, because again we're seeing square root of 2 over 2, minus square root of 2 over 2, minus square root of 2 over 2, positive square root of 2 over 2, positive square root of 2 over 2, and so on. So we can factor out square root of 2 over 2. Then we're going to have 1 minus x minus pi over 4 minus x minus pi over 4 squared over 2 factorial, then plus x minus pi over 4 cubed over 3 factorial, plus x minus pi over 4 fourth power over 4 factorial, plus, so it would be the square root of 2 over 2 times the sum as n goes from 0 to infinity of negative 1. Now this is a complicated one. Negative 1 to the n times n plus 1 over 2. That generates positive, then negative, then negative, then positive, then positive, then negative, then negative, times x minus pi over 4 to the n power over n factorial. And here is our Taylor representation of that. So we made it into a summation, our cosine into a summation. So I just need a note that n times n plus 1 over 2 sorry, negative 1 to that power gives us 1, negative 1, negative 1, 1, 1, negative 1, negative 1. Okay, so feel free to pause that. I'm going to move on here. Theorem 9.23. If the limit as n goes to infinity of r sub n equals 0 for all x in the interval I, then the Taylor series for f converges and is equal to this f of x equals the sum n goes from 0 to infinity of the nth derivative of f at c over n factorial times x minus c to the n. Okay? Okay, example 2. It says prove that the Maclaurin series for the function converges to the function for all x. We have f of x equals e to the negative 2x. So our f of x is e to the negative 2x. F prime of x is going to be negative 2 e to the negative 2x. F double prime of x is going to be negative 2 times negative 2 e to the negative 2x, which is 4e to the negative 2x. F triple prime of x is going to be negative 2 times negative 2 times negative 2 e to the negative 2x, which is negative 8 e to the negative 2x. So our nth derivative of x, I hope we can see a pattern here, it's going to be negative 2 to the n power e to the negative 2x. F of 0 is e to the 0, which is 1. F prime of 0 is going to be negative 2. Just putting 0 in there. So that's just going to be 1. You get negative 2. F double prime of 0 is going to be putting a 0 in there. You're going to just get 4. F triple prime of 0 is going to be negative 8. Seeing the pattern, 1, the negative 2, 4, the negative 8. We're multiplying by negative 2 every time. So the fourth derivative at 0 would have to be 16, and so on. So our, I guess we could say the nth derivative at 0 is going to be negative 2 to the n power. Okay, so our sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial times x minus 0 to the n power. That's going to be 1 minus 2x plus 4x squared over 2 factorial minus 8x cubed over 3 factorial plus 16x to the fourth over 4 factorial plus, and we see that going on. And that sum is going to be negative 2 to the n, x to the n over n factorial. And we see that negative 2 to the n. Here's our n factorial. Here's x to the n power. Now, 0 is less than or equal to the absolute value of r sub n. That's our remainder. So that if we were to stop at some point, this is what would be left over that wasn't added up. And that's going to be the n plus first derivative of f at z over n plus 1 factorial x to the n plus 1. So you may recall this from that section 9.7. That's going to be negative 2 to the n plus 1 e to the negative 2 times z over n plus 1 factorial x to the n plus 1. So if we look at the limit as n goes to infinity of the absolute value of negative 2 to the n plus 1, I'm just looking at this remainder, you can take the limit as n goes to infinity of e to the negative 2z over n plus 1 factorial x to the n plus 1. That's going to be the limit as n goes to infinity of 2x to the n plus 1 quantity. You could drop the negative because of the absolute values. Over n plus 1 factorial e to the 2z. And that will go to 0 because e to the 2z is going to grow faster than x to the n plus 1. And same thing with this n factorial, n plus 1 factorial. So, f of x, which is e to the negative 2x, could be represented by the sum as n goes from 0 to infinity of negative 2x to the n over n factorial. I should have done red so it stands out. There you go. So we can conclude that since the remainder goes to 0, that the function is equal to its Taylor. As usual, feel free to pause that. I need to scroll up. This is guidelines for finding the Taylor series. Okay, differentiate f of x several times and evaluate each derivative at c. Try to recognize a pattern. That's what we've been doing, trying to find a pattern. Use a sequence developed in the first step to form the Taylor coefficients. A sub n is the nth derivative of f at c over n factorial. So a1 is the first derivative, a2 second derivative, and so on. And determine the interval of convergence for the resulting power series. Within this interval of convergence, I wrote it twice, determine whether or not the series converges to f of x. So I look at the remainder. Okay. Example 3. This is find the Maclaurin series for the function. And it should say use the table of power series for elementary functions on page 684. So look this up in the text. So f of x equals e to the x squared over 2. Now we know e to the x, this is from the book. E to the x is going to be equal to the sum as n goes from 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. Oh, these are factorials. Plus x to the 5th over 5 factorial plus. So e to the x squared over 2, it's going to be the sum as n goes from 0 to infinity. I'm going to put this in place of my x. That's going to be x squared over 2 to the n power over n factorial. That's our sum as n goes from 0 to infinity of x to the 2n over 2n, 2 to the n, excuse me, over n factorial. That's the sum as n goes from 0 to infinity of x to the 2n over 2 to the n factorial. And that would be 1 plus x squared over 2 plus x to the 4th over 2 squared times 2 factorial plus x to the 6th over 2 cubed times 3 factorial plus x to the 8th over 2 to the 4th 4 factorial plus. So our series is x to the e to the x squared over 2 is the sum as n goes from 0 to infinity of x to the 2n over 2 to the n times n factorial. There we go. And really the key to it was we put this x squared over 2 in place of this x. Okay, again, feel free to pause. I'm going to go to example 4. This is our last example for this section. And that's the last example for chapter 9. Some people may be cheering right now as they watch this video. Some might be Sad, because they like Chapter 9. Okay, verify the sum. Then use a graphing calculator to approximate the sum with an error of less than 0.0001. So we're doing the sum. N goes from 0 to infinity of negative 1 to the n. 1 over 2n plus 1 factorial is sine 1. Well, for sine of x, that's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And this is in that chart on page 684. Plus x to the 9th over 9 factorial plus negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So sine of 1 is going to be, 1 goes in place of these x's. 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial plus 1 over 9 factorial plus negative 1 to the n times 1 over 2n plus 1 factorial. That is, this generates the odd terms. So we want negative 1 to the n times 1 over 2n plus 1 factorial to be less than 0.0001. We could drop the negative off because absolute value. So 1 over 2n plus 1 factorial needs to be less than 0.0001. So 1 over 2n plus 1 factorial needs to be less than, this is tenths, hundredths, thousandths, 10,000. 1 over 10,000. So that 2n plus 1 factorial needs to be less than, needs to be greater than 10,000. So if you look at all these, look at n equals 1, n equals 2, and so on. N equals 1, you're going to have 3 factorial, which is going to be 6. N equals 2, you're going to have 2 times 2 is 5 factorial, which is 120. And you go on down this, you'll see at n equals 4, well, I can just do it. N equals 3 is going to be 7 factorial, and that's going to be 5,040. So we're getting closer. And n equals 4, we're going to have 9 factorial, and that is 362,880, which means 4 terms will be appropriate. Because n equals 4, we're there. We have a very small error, because that is bigger than 10,000. So, sine of 1 could be represented as 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. And that's approximately 0.8415. And all we have to do is go 4 terms there. That's how quick you get that level of accuracy. Okay, well that'll do it for chapter 9. This is 9.10 into that. So send me your questions and I'll see you guys online. Have a good day.